Hi everyone, this is Mr. Lee. In this video, we are going to go over instantaneous velocity, but with calculus. Let's begin. So, as a quick refresher of what we did in class previous to these notes, we got a function, and we were able to discuss and talk about what it means to find the velocity for different points. So, for example, let's say we had a point here versus a point here, and let me use a different color so you can see the difference. So, we'll call this point B versus point A. So what we did in class is we took a look at point A and we said, okay, so if we take a look at point A, we can find the tangent line of that point. And if this is a position time graph, we're able to say, okay, so that tangent line is the velocity at that moment of time. And we were able to do the same for point B, where if we were to look at the tangent line at point B, we can say, okay, the slope of point B is the instantaneous velocity at that moment of time. So after we did that, we were able to create a velocity time graph with all those points, and we found that it was actually a linear line. Okay, now the idea with the instantaneous velocity and with calculus is instead of finding the instantaneous velocity at specific individual points, the power of calculus is that you could actually find the instantaneous velocity at a infinitesimal or every single imaginable point all along that curve. Okay, and so instead of thinking about like 1 second, 2 seconds, 3 seconds, you can be looking at 1.1 second, 1.111 second, 1.1111 second, right? So on and so on, right? So that's the idea of calculus. Now, in order to do this, we will be doing derivatives, and specifically for AP Physics Mechanics, our main focus will be using the power rule, and so that's what I wanted to show you today, the power rule. All right. So let's get some typing in. Now, for AP Physics, the power rule is written on part of your formula sheet, and it looks like this. We have d dx x to the n is equal to nx n minus 1. Okay, and your calculus teachers will do an amazing job at explaining exactly what all of that means. But what I want to do, and for the purpose of our class, because it's just an introductory part to calculus, right? Later on in the year, we'll get more and more calculus in. Is I just want to show you the shortcut method of the power rule, and more importantly, what that means. All right, so as a quick reminder, the slope of a position time graph gives us velocity. Okay, and so if we take the derivative, okay, so the idea of derivative is the slope. So instead of saying slope of velocity or position time graph gives us velocity, we can say the derivative of the position time function gives us the velocity time function. Okay, so what we're doing is we get to see how the object is moving, take the derivative, and with that derivative, that tells us exactly how fast the object is moving. Okay, so the position time function shows us where the object is, and the derivative shows us how fast it is. Okay, and then we can actually take this one step further, because the slope of a velocity time graph gives us acceleration. Therefore, the derivative of a velocity time graph or function gives us the acceleration time function. And we'll take a look at a couple of examples. So let's start. So the first example that I want to do is I want to show you a position time function. So we have position time, let's say it's 3t squared plus 2t plus, I don't know, let's say 4. All right. Now, a couple of things about notation. In calculus, you'll use a different notation than what we do in physics, and there is a reason for that difference. The reason that I like to use the physics version of the notation is that the notation actually tells you what the derivative gives us. So let's do a quick little example. If you take the derivative of a position function, okay, with respect to time. So let's break this down. So we have the position, okay, right there, with respect to time. time, what we essentially have here is, look at this, so that d is another way of writing the triangle. So we have dx over dt. And for those of you savvy at home, you know that this is the formula for velocity. So what this derivative notation tells us is the derivative of the position function with respect to the time variable gives us velocity. Okay, and so you'll see me using this notation in class because that notation tells us exactly what the derivative represents in terms of formula. Okay, now for the power rule. So the power rule, and once again, your calculus teachers will do an amazing job of explaining the ins and outs of the derivatives. But once again, I am just showing you the shortcut. So the rule of the power rule is you take your exponent. Okay, so if you have a variable and the variable is t, you take your exponent and you bring it out to the front. So it'll look like this, 2, and then you leave the rest behind. So 3t squared. But according to the official formula for the power rule up here, we see that your exponent has to be subtracted by 1. So I'm going to show that down here. So we brought down the exponent, which is a 2, and then we leave the rest behind, and then it'll be 2 minus 1. Okay? And then we'll do the next part of the function, plus 2t. Now, I'm going to leave the 2t there because that remains, but there is a hidden exponent right there, and the hidden exponent is the 1. Okay, so I'm going to bring down the 1. Now, once you get used to this, you're not going to show this step by step, but because this might be your first time experiencing the power rule, I want to show each step individually. And then here we have 1 minus 1. Okay, and then here we have a constant which is 4. Now, the idea is the derivative is taking a look at how much your variable or how much your position here is changing with respect to time. And this 4 is what we call a constant. And because it's a constant, that means it's not changing. So the idea of derivative is to see how much something is changing. And if something doesn't change because it's a constant, we notate that by saying it's a big fat 0. Or, in other words, it's not changing at all. Okay, so this line here is the uncleaned up version of the derivative, but if I were to clean it up, okay, I could write v of t because we know that we now have a velocity function, or we just want to keep it in the same notation, dx dt is equal to 2 times 3, which is 6, t, 2 minus 1, which is just 1. Now I can write that 1, but we know that the 1 is there, plus 1 times 2, which is just 2, times t, 1 minus 1, which is 0. Okay, now for this, t to the 0th power, hope you all know what that is. Okay, that is a 1. So what we end up with here, if we were to clean this up even more, it'll be 6t plus 2 times 1, which is just 2. And of course, we have this lagging 0 back here. So what this gives us is, let's say this function here, that function could look like this. Okay, it's like a parabolic curve of a position time graph. And if we were to take the velocity for all of those points along the curve, right, all of these points along the curve, what we would end up with is a linear line. And we know it's linear because here, this v of t, okay, this the time variable here, there are no exponents. So we know that it is linear. Now, if we were to take the derivative one more time, okay, well, remember the derivative, the idea of the derivative is you're finding the slope, okay, for all of these infinitesimal. We're finding the slope for all of this, but we know that because this is a straight line, the slope will not change. The slope will be a constant value. So when we take the derivative of this function here, we should get a constant value. So I'm just going to rewrite this function so that we can work off of it, okay, in a not messy version. So here we have dv dt, okay, which, just so you know, is the change of velocity with respect to time. Or another way of writing it is we are taking the second derivative with respect to position, and our time is squared, right? So this is all saying the same thing. And if we were to do the power rule here, remember up here we have the number 1. Okay, so it'll be 6 times the 1 times t, 1 minus 1, plus, and remember here, because there's no t there, there's no variable, that means it's a constant, and the slope of a constant is nothing, because nothing is changing, it's constant, we have a 0. So if I were to clean this up, we get 6 times 1, which is 6, t, 1 minus 1, which is 0, which is just 6. Cool. And remember what I said from the start, right? The derivative of a velocity function gives you your acceleration. And here, if we take a look at this graph up here, we see that the slope here is a constant, right? The slope isn't changing, unlike up here, where the slope in the beginning was nice and flat, but the slope at the end was nice and vertical. So the slope is changing, but here the slope is not changing. And so because the slope is constant, we see that the constant slope value was 6. And we represent that like so. So we have a constant acceleration value of 6. All right, so that's just the power rule in a nutshell. In class, we'll get plenty more practice in. I'll see you next time. Bye-bye.